Okay, so as I stated in the first part of this video, that if the particles are moving with the same speed v and u, then the chase is not going to end and there will be a final separation between the particles. So we'll pick up that part in this question, that particle A is moving in a straight line with a constant speed or constant velocity u, and particle B is always moving with a constant speed v, and the value of v is equal to u, and the velocity vector of particle B is always directed towards particle A. So what will be the separation or final separation between the particles? So you can see that suppose the final separation between the particles is x, okay, and at any general time t, suppose this is the position of particle A at any general time t, and particle B is moving along this curve when it is chasing towards particle A, when it is moving towards A. So this is the general position of particle B. So the line joining particle A and B is having a separation of small r at any time t. So the rate of change of this length AB at any time t r, dr by dt, we can write this as u cos theta, which is responsible for the increase in this length, and minus of v, which is responsible for the decrease in this length. So u cos theta is positive and v is negative. So you multiply by dt and rearrange these terms and integrate on both sides. Now the LHS term, which is integral of dr, you can see that r, which is the separation between the particles, the initial separation was d and the final separation is going to be x, right? The chase is not going to end now. So the final separation will be x, not 0. So in this integral, you will get x minus d equal to u is a constant. We can bring it out of the integration. And integral of cos theta dt minus again v is constant. You can take it out of the integration. And integral of dt is capital T. Now the next equation, as I told in the last video, that the next equation we have to find by taking the projection of this path of particle B along the straight line which was followed by particle A. Okay, so you can see that particle B was initially at this position, this is t equal to 0, and at time capital T, the particle B is at this position. Whereas whereas particle A was at this position at time t equal to 0, and in capital T time it reached this particular point over here. So what is the displacement undergone by particle A along the straight line? So from initial position to this position at time capital T, we can write this entire displacement as u into capital T. And for particle B, you can see that the projection of this curve along the x-axis, this will be the length of projection. You can see this length over here. This will be the length of projection of the curve taken by particle B along the path of particle A. So you can see again, you must go through the last video where I had explained regarding the projection of a curve on a straight line. So the displacement that particle B undergoes only along x-axis in time capital T, that displacement is from this initial position till the final position of B at this point. So the velocity of B along the x-axis is v cos theta. So integral of v cos theta dt from 0 to capital T is going to give me the displacement of B along the path of particle A in time capital T. So you can see we can relate these two distances as ut, which is equal to x plus the displacement of B along x-axis. So u2 equal to integral of v cos theta dt plus x, right? So again, you can replace the cos theta integral cos theta dt term from this second expression into the first expression, and you are going to get this expression. I've just replaced integral cos theta dt into this first term. Now, since the value of v and u was same, these terms gets cancelled out. Okay, and you will be left with x equal to d by 2. You can solve this particular expression. Just remember that v is equal to u for solving this equation, and you will end up with this result, which is the final separation is d by 2.